An oblique, or sometimes called slant asymptote, occurs when the top degree, in this example, the highest degree of the top polynomial is a 2, is 1 greater than the bottom degree. In this case, the bottom degree is 1. It could be 3 and 2, 4 and 3, just wherever the top degree is 1 larger than the bottom degree. That can cause what we call a slant asymptote, which is just a slanted line that the graph will come close to but never cross over. The way you determine the linear equation that's going to match that slant asymptote is by dividing the bottom into the top. And you can use long division or monomial division or synthetic division, whatever works for that particular case. I'm going to choose to use synthetic division in this case. Long division would look like this, and synthetic division for that matching problem would look like this. So if we bring down the first number, multiply, add down, multiply, add down. This is the remainder, this is the constant, and this is the x to the first term. Now the interesting thing with slant asymptote is you don't have to worry about the remainder. It doesn't matter what the remainder is, so we'll just forget about the remainder. And even if you do long division, you'll get 2x plus 1, and you eventually down here would get a remainder of 5. You don't worry about that. You just pay attention to what's on the top, and that is going to be the equation, your linear equation for that slant asymptote line. And again, this is 2x plus the constant 1, and we don't care about the remainder. So if we consider how to graph the slant asymptote, which is y equals 2x plus 1, remember that 1 is the y-intercept, and so we'll put that there. And then the 2 represents the slope, which we could put over 1 so that we have a rise and a run. So we rise 2, run 1, rise 2, run 1, and we get this slant asymptote. And we want to make it a dotted line because it's not really part of the graph. It's just going to be a line that our graph approaches. Now we do still need to look for vertical and horizontal asymptotes as discussed in another lesson. And there is no factoring that's going to be done on the top to where we can cancel out any factors, so there won't be a hole. But there will be a vertical asymptote, which is where whenever you make x minus 2 equal to 0, whatever that is, which is x equals 2, will be your vertical asymptote. So we're also going to have a vertical asymptote at x equals 2. Whenever the top degree is bigger than the bottom degree, you won't have any horizontal asymptotes, so we're ready to graph. And if you needed to look at a table or create a table of values so that you can find where this graph is going to go, what's going to happen is we're going to end up in this region and this region. And that is where our graph's going to be. It's going to have to stay inside the lines of the vertical asymptote and the slant asymptote. Another point that's a good point to find if you're not using a table and you just want to get the general idea of it is the Y-intercept, and that is whatever happens when x is 0. And so if you let x be 0, you end up with 3 on the top of your equation and negative 2 on the bottom of your equation. So that negative 1.5 is the y-intercept. So I'm a little off here because really I should be going through this point right here at negative 1.5. So my graph should be like this instead. And again, if you're trying to find some more points to make your graph a little more accurate, you would make an XY table or look at a table in your calculator, put in different values for x into the original equation, find out what the matching values of y are, and you could get a whole bunch of points to graph and find the red graph more accurately. But I can tell you this is what it's going to look like. There's going to be a piece down in this corner, and there's going to be a piece up in this corner, and that is the only place where you're going to have graph.